Good morning, students. Welcome to video lecture on microwave and optical fiber communications. Subject code U18EC709. Topic photodetectors. Photodetector. It is the first element of optical receiver. It converts optical signal into electrical signal. It is the block diagram of optical receiver where it converts the optical light into electrical signal. In optical receiver, photodetector followed by front-end amplifier, filter and equalizer, sampling circuit and decision circuit. There are several photodetector types: photodiodes, phototransistors, photon multipliers, photoresistors. Requirements of photodetector: responsivity, bandwidth, dimensions, noise, temperature and cost. Good sensitivity or selectivity at the desired wavelengths and poor responsivity for the other wavelengths, and it should have a good wavelength selectivity, required wavelength selectivity. A photodetector should have fast response time and also have high bandwidth, compatible physical dimensions. It should offer low noise, insensitive to temperature variations, long operating life and a reasonable cost. You can observe the instant of photon, how it can be converted into electrical current. Photodetector. Due to above requirements, only photodiodes are used as photodetectors in optical fiber communication system. The types of photodiodes used in optical fiber communication are pin photodiode, and avalanche photodiode, APD. The first one is pin photodiode. It is the structure of pin photodiode. The device structure consists of P and N regions separated by a lightly doped intrinsic region. In normal operation, a sufficiently large reverse bias is applied across the device so that intrinsic region is fully depleted of charge carriers. Now here it is PIN is the structure of photodiode. The P-type device is connected to the negative supply of the battery, and N-type material is connected to the positive supply of the battery, so that the device is reverse biased in such a way that the intrinsic region is depleted of charge carriers. Means there is no free electron and hole present in intrinsic region. Now, when some photon instant in the intrinsic region, here when an instant photon has energy greater than or equal to the band gap energy of the semiconductor material. It breaks the covalent bond and generates electron hole pair in intrinsic region. The instant photon breaks the covalent bond in intrinsic region so that free electron hole pairs get generated. The photodetector is normally designed so that these carriers are generated mainly in the depletion region where most of the instant light is absorbed, and the process generated free electron hole pair which are known as photocarriers since they are photon generated carriers. The high electric field present in depletion region cause carriers to separate and collected across the reverse bias junction. The generated carriers will move across the reverse bias junction. This gives rise to current flow in an external circuit, and the current is known as photocurrent. It is due to photocarriers. As the charge carriers flow through the material, some electron hole pairs will recombine and disappear. Uh, the generated charge carriers will move in N-type and P-type material. Some of them will recombine and disappear, and the remaining will responsible for photocurrent. On the average, the charge carriers move a distance Ln and Lp for electrons and holes respectively. The distance is known as diffusion length. Means here after breaking the covalent bond, the electron hole pairs gets generated and travel towards the Pn regions, and here before recombine they travel some distance. In case of electron it is Ln, and in case of holes it is Lp. The time it takes for electron or hole to recombine is known as carrier lifetime. That is from the generation position to the time at which they recombine is called the carrier lifetime of electron or hole, and they are represented by Tp and Tn for electron and holes respectively. The lifetime and the diffusion lengths are related by the equation 1. Ln is equal to dn tau n power 1 by 2 and Lp is equal to dp tau p power 1 by 2, where dn and dp are the electron hole diffusion coefficients. If the photon region has width w, then the total power absorbed in the distance w is given by P of w is equal to P naught of 1 minus e power minus alpha s multiplied by w. It is the width of depletion region, and where alpha s is the absorption coefficient at frequency lambda. The primary photocurrent resulting from the power absorption in equation 2 is given by Ip is equal to Q by h mu P naught 1 minus e power minus alpha sw multiplied by 1 minus Rf, equation number 3, where P naught is the power optical power instant on photodetector. Rf is the reflectivity at the entrance phase of photodetector. Q is electron charge, h mu is photon energy, Ip is average photo current. The next concept is quantum efficiency. It is represented by eta. The quantum efficiency of photodetector is given by the number of ratio of number of electron hole pairs generated to the number of incident photons. That is, if you observe the structure P I N, when some photon energy is instant on the intrinsic material, it generates electron hole pairs. Now it is the quantum efficiency is the ratio between the electron hole pairs generated in intrinsic region to the number of instant photons. It is given by equation number 4. And to achieve high quantum efficiency, the depletion layer or region must be thick enough to permit a large fraction of instant light to be absorbed. Here in intrinsic region, if the more energy is absorbed by the intrinsic material, more number of electron hole pairs gets generated. In turn, will increase the quantum efficiency of photodetector. However, the thicker the depletion layer, the longer it takes for the photo-generated carriers to drift across the junction. Means the generated carriers, if the depletion region is thick, then it takes longer time uh, to drift across the junction. Since the carrier drift time determines the response speed and the quantum efficiency, the performance of photodiode is characterized by responsivity. If the width of the depletion region or the intrinsic region is more, uh, the device is having a less responsivity. And the formula for responsivity R is given by IP by P naught. It is equal to eta Q by H mu. Eta Q is quantum efficiency. And the primary current is equal to uh, R into P naught. It is a product of responsivity and the incident photon energy, photon power. Sample problem. Refer to the formula to solve the problem. One more sample problem. Same, follow the formulas to solve the problem. The next is avalanche photodiode. It is the structure of avalanche photodiode. In case of conventional pin photodiode, the output current is very small and the gain is less than 1. Gain means carrier multiplication in intrinsic region. To increase output current and gain, avalanche photodiodes are used. APD structure P plus pi P n plus, that is P plus pi means it is intrinsic region, P n plus means it is highly doped. Here plus is not included, means it is moderately doped. The intrinsic region P doped for imperfect purification. Light enters the device through the P plus region and it is absorbed in pi material. Here it is on the instant photon. It is it enters the P plus region and it is absorbed by intrinsic material. The photodiode is designed to operate near the breakdown voltage. Near means it should be operated below the breakdown voltage. The instant light will produce electron hole pairs. These carriers travel with saturation velocity, means high velocity. In order for carrier multiplication to take place, the photo-generated carriers must traverse in a region where a high electric field is present. In this high field region, a photo-generated electron or hole can gain enough energy so that it can ionize bound electrons in the valency band upon colliding with them. This process is known as impact ionization. The newly created carriers are also accelerated by the high electric field, thus gaining enough energy to cause further impact ionization, and this phenomenon is called avalanche mechanism. Means here it is valency band, it is conduction band. With the application of photon energy, the diode is already reverse biased slightly below the breakdown voltage, and when the application of photon energy, it breaks the covalent bond and generates electrons and hole pairs. The generated electrons acquire saturation velocity and they collide with the other atoms to generate electron hole pairs, and once again the generated electrons acquire high energy, they collide with the other atoms, and here the generation of electron hole pair is called impact ionization, and the carrier multiplication process is called avalanche mechanism. And the diode is operated below the breakdown voltage, finite number of carriers are created, and if the diode is operated above the breakdown, then infinite number of carriers gets generated. And for perfect operation of a avalanche photodiode, it should be operated slightly below the breakdown voltage. Now, the photo-generated carriers drift through the pi region in the Pn plus region where high electric field exists. The generated electron will enter into Pn plus region. The multiplication M for all carrier generated in the diode is defined by Im is equal to Im by Ip. Im is the carrier multiplication current, Ip is the primary current. Responsivity RAPD means for avalanche photodiode, it is eta q by h mu multiplied by M. The only difference in pin diode and avalanche photodiode is the multiplication factor. It is equal to R naught into M. R naught is unity gain or responsivity. Thank you. We will meet with the next lecture.